Okay, so thank you for the introduction. So as said, I'm Michael Ortega, and I will present you a work made in collaboration with Alix Goguey. We are both from the University of Grenoble in France. And this work is about BEXHI, a new mechanical structure for prototyping new interactions on handheld devices with the specificity of having bendable and expandable features. So this work can be considered as part of the organic user interface research area, introduced in 2008. And if you look at the Wikipedia page of this research area, you will find that there is mainly three types of OUIs. The first one is flexible user interfaces. So with flexible user interfaces, your display is flexible. So you can use the flexibility to interact, so the flexibility gesture to interact with your application. With the shaped user interfaces, the display is not a square, flat display anymore. It can take any form in 2D or in 3D in order to better support the main function of your application. And finally, the actuated user interfaces are interfaces that where the shape is controlled by the system itself. So if you look in the literature, there is a lot of benefits with these kind of features, and especially for handheld surfaces. Like, for example, here with the flexibility feature, you can interact with your device, and it's occlusion-free, so that means that you made interactions and you do not disturb your screen. You can also combine it with the touch interaction, etc., etc. With the shaped user interfaces, you have some kind of adaptations of the shape of the device. Like, for example, you can adapt it to the interaction resolution, to the context, to the user, and also to the content. So let me give you an example of this. Here, I want to display a panoramic image on my mobile phone. So I have several solutions. The first one is I display just a part of the image, but I do not enjoy my panorama. The second one, I display the complete panorama on the phone, but I have these dirty bars on the top and the bottom of the panorama, and the panorama is quite small, so I cannot enjoy the full resolution of my screen. So the last solution I have is I change the form factor of the image, but here it's not a panorama anymore. So what we would like to have, and that could be very nice, is to have some kind of device that can expand in one dimension. And here I can keep the good aspect ratio of my panorama and enjoy my panorama. So as I told you, there is some devices with the flexibility feature, which are very nice. Also some devices with the expansion. But for now, there is no device that combines these two features. And beside the fact that if you have such a device, you could have both advantages of these features, you could also have new ones. For example, you could have new shapes that combine the flexibility and the expansion. Like, for example, here you see like it's flexible, but I cannot expand, so I cannot do all the shapes I want. So new shapes, new gestures. So we aim at investigating these new kind of devices. But the first question is, how do you prototype this kind of device? So the first solution we had was to investigate low-fidelity prototypes. So this kind of approach is quite nice because you can validate the first hypothesis you have very quickly. But how do you do expandable and flexible devices with these kind of prototypes? The paper is nice because it's flexible, but you cannot expand paper. The cardboard, you have the same problem. It's flexible, but not expandable. So you could imagine some laser cut patterns to make the cardboard expandable just a little bit. Sorry. But the expansion will be very small, and you will have to deal with porosity, so your prototype will have a lot of holes on it. We also tried fabric. So with fabric, you have the flexibility, you have the expansion with some fabrics, but the problem with fabric is you need a frame because the fabric does not self-support itself. So you could mix it with some structures like the one I presented before or a simple frame, but you will also have a lot of problems. Like, for example, on concave shapes like this, the fabric will always take the shorter path, so it will take off from the structure. You will also have some wrinkle effects because fabric is very supple. So you will have to paste your fabric on the structure, and then here you are losing the expansion and it's quite dirty, etc., etc. So finally, we decided to turn the page, and instead of investigating low fidelity prototypes, we investigated higher fidelity prototypes. So this is what I will present you today. So we started from our previous work called Exhibit. So with Exhibit, we already deal with expansion as a mechanical structure. So let me show you a video of an Exhibit device prototype in only one dimension. So you can see that Exhibit is an assembly of units that can slide from each other. Each unit is made of layers. You have plexiglass layers that make the interweaving structure of the device, and you have a paper layer on the top in order to project on your device. So with tracking and projection, you can simulate an expandable device. This is the 2D structure of Exhibit, and in blue I put the interweaving layers. So I can show you here with only these layers how it behaves in 2 dimensions. And okay, so here the 2 dimensions are linked, but you can separate them, and you can also make some rotations in order to have non-square surfaces like trapeze. So here is a small video where we assemble several surfaces, Exhibit surfaces, to make a cube. And you can see that we have volumetric objects that can expand in the 3 dimensions independently. Here is the Exhibit cube in context, where we project a building on it. We simulate a building with different floors, and it's a kind of architecture scenario where you try to find a good place and the good size of your building in a town. Okay, so Exhibit works well, so it's a higher fidelity prototype. It works well for expansion, but the main question now is, how do you integrate flexibility? How do you make it flexible? So for this, we had to deal with 2 things. First, the interweaving structure itself, and the covering layer. So first, the structure. So we decided, after several thinkings, we decided to make the fingers flexible. So by fingers, I mean this part of the interweaving layer. So you have the main core and the finger. So the first solution we tried was to laser cut the plexiglass, like this. So we made some pattern on the finger, and then this finger becomes flexible. So it works. We made a prototype with this, but it was too brittle. With this size of the plexiglass, it was too brittle. And also, we had another problem, is that the sliding was discrete, so it was not very, very good. So we decided to investigate another solution, and we used another material for the finger. So here you have a 3D figure of the new layer, of the BEXHI interweaving layer. So you can see that we kept the main plexiglass core in blue, and the white part, the fingers, are printed in 3D with a 3D printer and in flexible plastic. So from this, we made our first prototype, a tablet. So you can see here the dimensions. In the center, you see squared units, and on the borders, we simulate some kind of bezel. And here a small video about how it behaves. So it's not brittle at all. It works quite well. It's very, very, very flexible. And you can imagine new shapes. So here from the back, you can see how it works. So the plexiglass, transparent plexiglass, and the white stuff are the printed fingers. And here you see the flexibility and the expansion of each finger. So after this, we had to deal with the covering. So as you can imagine, if you paste the paper like we did with Exhibit, you will have this kind of effect. So the paper, as soon as you use convex shapes, the paper will take off from the surface. So for avoiding this, we first tried to come back to fabric again, but we also had the same issues with the shorter path, the wrinkle effect, so it was not very good. We also tried to use plastic tiles with preformed curves in order to always keep the tile pasted on the surface, but it was a very long building process, so very bad for prototyping. And we also had a bad effect on the surface. It was not flat anymore. So we decided to come back to paper and to use magnets. So here you can see the same picture than before, but you can see on the corners of the tiles that there is some magnets. These magnets are very thin, square magnets. They are pasted on the tile, and for making it pasted on the surface, we add a metallic layer on each unit. We also had to deal with something new, according to Exhibit. With Exhibit, we only had extension. Okay, so the size of the tiles was predefined and was only the size of 2 units. But here, as soon as you have the flexibility added to the expansion, the distance between the between 2 units is bigger, is longer. So we had to deal with larger tiles. But it's not only printing larger tiles. If you have larger tiles than the previous one with Exhibit, you had to deal with collision between the tiles. So I invite you to read the paper about all the details, but we had to create new shapes for the tiles. And here you have an example where you can see on the right that even when the surface is closed, there is no collision between the tiles. So finally, this is the new structure, so the structure of BEXHI. So it's like EXI, but with a B for bendable. In green, you have the new layers, or the layers we modified. And I want you to see that we also add another layer, the layer 8, which is the yellow stuff here. And this layer arises from some experimentation. So after doing the first prototype, we thought that it could be very interesting to expand the surface locally. So I mean, instead of expanding the complete surface like that, it could be very interesting to only expand a part of the surface. So for doing this, you need a grip for that. So we had also a new layer, a grip layer for manipulating the Exhibit surface. So to conclude, this is a small video about how it works. So you can see these new shapes. So this is a fan. You can only have it with expansion combined with flexibility. You have these kind of waves, and you can see that the tiles always stay on the surface. And that's it. So thank you for your attention. So, and if you have questions.
Thank you. That's very interesting. So do we have any questions from the audience?
Hello. Thanks for your presentation. Do you have any, presentation after you're making this device? For example, that panorama you showed. I want to know what could be the quality of the screen and the presentation of, for example, that panorama image that you showed.
What do you mean by quality?
So you try to stretch the screen, yeah?
Yeah, stretch and bend the screen, yeah.
So do you have any example of, for example, an image after you stretch the device?
After I stretch the device?
So it could be used in, for example, mobile devices, yeah?
Yeah.
So if it is applicable, consider I want to see a image of a panorama image in that screen of that mobile phone. Yeah.
So
how could it be?
So you are talking about it's more or less the application we could have with this. So, well, for now I can show you a very small video about some first investigations. So, for example, here we try to investigate. It's for future work, but we try to investigate the bending resolution you could have depending on the expansion. For example, here, according to the expansion, the resolution is different. But as you can see, the image is always the same. We do not modify the image itself. Mm-hmm. We use it at input interaction. We also thought about changing the image, but well, I have an example in mind, but I cannot tell you because it's submitted to Kai. So
I wanted to see this. Thank you.
So this is the first example.
Thank you.
And for now, we just project the image and do not change.
It will not affect quality of.
No.
Okay. Thank you.
Well, it could affect something. Of course, if you have a bendable device like this one. If you make the complete bending, you cannot see the whole surface, so it affects a bit the quality of your seeing of the scene, of course.
So, in case you just project the image over your prototype.
Sorry,
so you just project the image over your prototype.
Yeah, exactly. So we track the prototype and we project it, the image on it like a texture.
All right. We have another question.
Hi, I'm Raimund Axfeld, Interactive Media at Dresden. This is very nice work. It's a great piece of engineering. I'm a little bit concerned that it is only now that you show us this video. So some application, I think it would be good to not just do the engineering stuff and show that, but also what you can do with that, just as a comment.
Yeah, so it's a short paper, so we submitted the prototype for us, and we will investigate applications for
it. Okay. But my question is a little bit, don't you think that's a bit complicated? For example, if you also cite Jürgen Steinmel's FlexPad, and they use a special foam basically, so they are not able to expand their surface, but they can bend it quite freely. So my question is it really necessary to have such an advanced device? Or would it also do to just have several of these flexible, bendable...
I cannot answer this question if it's really necessary. So we made a prototype for answering these questions, for making new interactions, and to answering if it's necessary to having expansion or not. So that's why we published this kind of prototype. We hope that a lot of people will use it and say us, okay, so expansion is not a good idea, combination is not a good idea. So I cannot answer the question of if it's usable or not.
You said about using it, so do you make it available, the details, the details of the construction?
I didn't put the reference on the slides, but it's available. So you can have the maps for cutting, the plexiglass, for printing, so it's all available, yes.
Okay, thank you very much.
Any other questions?
Really interesting structure and work. Thank you. My name is Young Boshin from KAIST. I'd like to ask you for an kind of additional explanation on your grip structure, because I think the concept of using partly expanding the structure is really interesting and also an important idea. So could you give an additional one?
Okay, so you want me to explain how I did the grip? So it's printed in 3D. So we use a 3D printer. So the structure of the grip is also available. It's an STL format, so you can print it.
Oh yeah, I was meaning to because you explained the grip is for partially expanding the device. So what was how does it work, or like things like that?
How does it work?
Mm-hmm.
So, well, usually we wanted to keep the idea that when you, if you want to interact with a handheld device, you don't want to occlude the surface. So you just have the bezel to interact with. But you could also imagine to interact from the back. So that's why we add these kind of grips in order to allow you to make more precise interaction, more precise expansion. So these grips are only on the back, so you do not disturb the display on the front.
Oh, so it means it's literally a grip, right?
Sorry, what?
So it's literally a grip.
Yeah.
I think I misunderstood. Like it could be used as a lock to like just partially lock some parts of the modules. So you could expand only parts you want.
No, we put the grips on all the back of all the units, so you have to choose according to your application.
Okay, thank you.
Okay, let's thank our speaker once again. So